Unit 1, Lesson 2, Practice 1.2.1, Differences between Populations and Samples. So, number 1, which statement explains why a state government would use population parameters, the number of votes cast in the entire state, rather than samples from each county to determine the outcome of an election for governor? So remember, samples are a smaller group, population is a whole group, and parameters are what you're looking at, okay? The number of votes. So modern technology makes it quick and easy to count votes? Should, but it doesn't seem that way always. A sample only represents a portion of the entire population. A gubernatorial, that's a mouthful, election is too important to decide based on estimates from sample statistics. It takes much longer to count the votes in a sample than in a population. Not every eligible person votes. Okay? Well, we obviously want to do this because we want everybody to we want everybody's vote to be counted. If we're doing a sample, that doesn't always represent the whole, the population. Which statement explains why sample statistics are used by the media to make predictions prior to presidential elections? Percentages are difficult to compute with large numbers. No, just as easy. Sample statistics are more reliable than population parameters. No, because a sample is going to represent the whole population, so if you can get the whole population, why not do that? Members of the Electoral College determine the outcome of a presidential election rather than the popular vote. That's true, but not necessarily why the media does it. It would not be practical for the media to determine every person's opinion prior to the election. Boom, right there. That's what we have elections for. Which statement best describes the effect of sample size on statistics? Okay. A statistic obtained from a large sample gives a more reliable estimate of a population parameter than a statistic obtained from a small sample. From a large sample gives a less reliable than a small. So those ones are opposite each other, aren't they? A statistic obtained from a large sample has greater variability than the variability in the original population. Okay. The original population is always going to be more varied than a sample, so definitely not that. A statistic obtained from a large sample has greater variability than a statistic obtained from a small sample. Okay, that one is true. So, honestly, it could be A or D. The larger the sample, the more variability, the more like the population it's going to be. Okay, than a smaller one. So I'd probably say D seems to be the one they want us to go for, even though I like A. Okay? I like the idea of variability as opposed to reliability, talking about that. But I'd accept either one. So yeah, either one of those. I like them both, so I would pick either one. Looking at the answer sheet, I think it said A, but I like both of those. Either one would work for me. Okay, so for a science project, Tyrus tested 40 sun-charged brand batteries to estimate the mean time that sun-charged batteries last. Identify the population, the parameter, the sample, and the statistic of interest in the situation. So remember, population is the total, everything. So that would be the batteries, all of them. Okay? The sample would be the 40 that they actually tested. Okay? Out of all of those batteries. The parameter is how long do their batteries last, okay? And the statistic of interest was the mean time in those 40. Alright? So that's essentially what we're doing for the rest of them. So number 5. Maggie distributed a survey to the students in 5 homerooms to estimate the percent of students at her high school who are in favor of the new dress code. Identify the population, the parameter, the sample, and the statistic of interest. So remember, the sample and the statistic of interest are connected, just like the population and the parameter are connected. Same with the statistic of interest and the parameter are connected, as well as the sample and the population. So she distributed a survey to 5 homerooms. Okay, so those students in those 5 homerooms would be the sample, because she wanted all of her students at the high school. So that would be the, oops, and I colored them wrong, didn't I? So that's the sample, the students in the 5 homerooms, and the population is all the students. Okay, and they're talking about being in favor of the new dress code. So the parameter is who is in favor of the new dress code, and the statistic of interest would be those within the 5 that are in favor of the new dress code. In a marketing survey, 13 out of 80 participating adults reported that they would like to purchase a new cell phone in the next month. Estimate the number of adults in a community of 7,200 adults who would like a purchase to a new cell phone in the next month. Assume that the sample is representative of the population. Because we're assuming that the sample represents, I know that 13 out of 80 would like to purchase a new cell phone. I want to know how many out of 7,200 would like to. So I create a ratio here. Okay. Then with a ratio, it's fairly easy. I can just multiply both sides by 7,200. Okay, that would be 1. So then that's what I would multiply with my calculator. I type that in, and we get question mark equals 1,170. So 1,170 people, I can estimate that they would want a new phone because of the 13 out of the 80. Okay. So number 7, in a wildlife study, 12 moose in a given region were released with tracking devices. Later, 20 moose were found in the region, and 4 of them had tracking devices. Use the results to estimate the number of moose in the region. Assume no moose entered or left the region during the study. Okay. So we had 12 given tracking devices. 20 moose were found, and 4 of them had tracking devices. So 4 out of 20 had tracking devices. So if we gave 12 moose, okay, so we want to know 12 out of how many. So then we set another ratio, and another way you can do it is by cross multiplying. That's the same way, but we'd go 12 times 20, which would be 240, and that would be equal to 4 times question mark. So we divide by 4. 240 divided by 4 would give us 60. So we would estimate 60 moose in total. Alright, so we have some information for problems 8 to 10. So, the director of a community health clinic is compiling information on the total blood cholesterol levels of all the patients who regularly visit the clinic. 1 week, 27 male patients and 23 female patients had their blood cholesterol levels measured at the clinic. The results are shown. So remember, in a box and whisker, these are your biggest number. These are your smallest. The median is right here in the middle of the box. And then the median of the first half of data is right here, called the first quartile. And the median of the second half of data right here is called the second quartile. Okay. So we also have this information. The population size, so the total number. The people sample size, the ones they were dealing with. Their mean and standard deviations. And then the number that had the greater cholesterol. Okay. Use the results in the table to estimate the number of male patients at the clinic with a cholesterol level greater than 150. So we want a ratio again. So I'd say 20 out of the 27 had the greater. So we would go, how many out of 343? So I can cross multiply again. So 20 times 343 equals 27 times how many? So 20 times 343 is 6,860 equals 27 times question mark, divide by 27, and we get 254.07, so we just round, since it's people, 254. Okay, use the results in the table to estimate the number of female patients at the clinic with a cholesterol level greater based on the sample. So same idea, just with the female numbers. So it'd be 14 over 23 would equal what over 298? So we cross multiply. 14 times 298 would equal 23 times question mark. 14 times 298 gives us 4172 equals 23 times question mark, divide by 23. Sorry, I'm writing over everything. Would give us 181.39, so 181 females. And this was males. Okay, now it says estimate the mean cholesterol level of all the clinic's regular patients. Assume that the observed differences between males and females can be attributed to sampling error. So for an estimate, I would simply, because these numbers are fairly close, I would just take the 167.6, 179, and find the mean between those two. Okay, so 167.6 plus 179 would give me 346.6. Divide that by 2, we would get 173.3 milligrams per deciliter. Okay. So if I really wanted to get specific, I would have to figure in the differences in numbers and that kind of stuff. Okay. So that's what we'd end up with. All right, there we go. That's all of it.